Hello everyone. In this video, I will be talking about machine learning fairness and how adversarial learning can make models more fair. Specifically, I'll visually explain a model written by David Madras et al. That can create fair representations out of datasets. So first things first though, what is machine learning fairness? Well, I'll explain this through a toy example. Imagine that you're a researcher at your hometown university and you have personally collected a dataset of X-ray images from various patients. In your dataset, you have patients who come from a high economic class, who are colored in blue, and patients who come from a low economic class, who are colored in green. Now, your goals with this dataset are to use it to diagnose patients and also to distribute it to machine learning engineers and researchers around the world. However, you want to make sure it's not used in any harmful applications, either deliberately or by accident or some mad scientists out there. To test whether or not this dataset can be used in a negative application, you create and train your own machine learning model as your way of doing a sanity check. Now, after your model is trained, you try passing in two test data samples, one from a high economic class patient and one from a low economic class patient. The thing about these two samples in particular, though, is that their X-ray and metadata are almost completely identical. So, you expect them to return the same kind of prediction from the model. You go ahead and you pass in the high economic class data through the model, and you get a correct prediction. Okay, cool. How about the low economic class data? Wait, you get an incorrect prediction? That doesn't make any sense. The two patients have exactly the same X-ray data and almost exactly the same metadata. Why is this model more accurate for the high economic class group than the low economic class group? You may think that this is just some toy example that describes some one-off case, or that the model that I've presented here has some bug in it. But an investigation was done by Syed Kalinatari et al., where they ran state-of-the-art machine learning models on vastly large X-ray datasets. And in doing this, they found a statistically significant disparity in true positives across a high socioeconomic group and a low socioeconomic group. So this problem, where the high economic class group is being more accurately classified than the low economic class group, has been seen in the real world in a statistically significant way. Why is it happening? What's going on here? Well, if we jump back to the model's training stage and do some investigation, we could see that the model is putting a lot of weight on the economic class feature for the green data samples. Now, it makes sense why the model might want to look at this. Maybe people from lower economic class groups may not have access to as high quality healthcare as people from high economic class groups. Also, perhaps there could be some biases in the human generated dataset, which makes this feature seem more prominent. But regardless, we do not want our model to learn from this dataset in this way. We want it to be fair, that is, equally accurate with respect to the different economic statuses. In addition, we want the model to look mostly at the X-ray images, not at the economic statuses. After all, that's where the key information lies to making these diagnostics predictions. So we want the model to be more fair, and we want it to not consider this economic class feature so heavily. How can we concretely define our goal? There are a few definitions of fairness, each with their own pros and cons. Here, we'll be talking about three definitions in particular. First, some notation. Let P of y equals y hat be a probability mass function that represents our model making a prediction y hat, which can be either 0 or 1. Also, let z represent our protected variable, which is the variable that we want to reduce our dependence on. In our toy example, z represents a patient's economic status. One definition of fairness is demographic parity, and this tries to enforce that predictions are independent of the protected variable. Concretely, this means that the probability that you make a prediction is going to be the same probability making that prediction given this protected variable. Now, this makes sense, and it kind of sounds like what we want. But there is a downside. We mentioned before that patients from a lower economic class may not have access to the same kind of healthcare resources as patients from a higher economic class. So it may also make sense that the probability of a patient being healthy given that they're from a high economic class is not equal to the probability of a patient being healthy given that they're from a low class. Using demographic parity will remove this information from our model, and we don't want to throw away that information because it's useful in making predictions. This motivates the next two definitions of fairness, the first of which is equality of odds. This tries to enforce that the predictions are independent of the protective variable given any target. So it looks similar to before, except we're given a label y, and the probability that you make this prediction given this label is going to be equal to the probability that you make this prediction given the label and the protected variable. Equality of opportunity is very similar, except it's putting this independence on a particular preferred target. So here, there is a single label y, which is either 0 or 1, healthy or unhealthy, and the probability of you making this prediction is independent with respect to that variable y and your protected variable. Now, the difference between equality of odds versus equality of opportunity is that the latter requires a non-discriminatory case only within the advantaged outcomes. Now, this may seem silly in the context of X-ray images and patient diagnoses. However, equality of opportunity brings upon a useful insight in other problems, such as university admissions or bank loans. Another important thing to note is that you can only achieve one of these three fairness criterion above, as achieving one will contradict the other two. Each fairness criterion has their own pros and cons, so it's up to the user to figure out which one they want to implement. Okay, so we've defined our definitions of fairness in a more rigorous way. Now, what can we do to our data set so that the models trained on it will be fair? Is there some sort of answer that we can have so that we can make sure that no evil mad scientist will use our data set for no good? Well, there is an answer. The answer is laughter. Learning adversarially fair in transferable representations. Okay, bad jokes aside, laughter is a model proposed by Madras et al. In 2018. And effectively, this is an adversarial model that aims to re-represent the data in a latent space so that it's hard to predict the protected variable, but still easy to classify the right predictions. Now, it looks very complicated right now, but I'll walk through an example step by step. So imagine that you have one of our X-ray images, and imagine that this laughter model is trained completely. We'll start by passing in this X-ray image to the input value, and that will be represented by X. We'll feed X to the encoder component of laughter, and in return, we'll get a latent representation of this data, Q. Now, this Q variable is interesting. We can use it through our classifier to make our predictions y hat, but also we will pass Q to a certain adversary. Now, this laughter model that we present right now is fully trained, and we've trained it so that this adversary is very, very good at trying to pick out the protected variable in this latent space. But we've also trained our encoder to be very good. In fact, we've trained our encoder to be so good that it's able to encode all of the information in X into Q, such that it's very hard for the adversary to guess what the protected variable is. In fact, the encoder does such a good job that the adversary basically just guesses as to what the protected variable is, as it has no idea. Finally, Q is passed to the decoder, which tries to reconstruct X from Q, so that we know that the latent representation of Q encodes all the necessary information needed to get X. So that's how laughter works. The main ideas of laughter are to train a powerful encoder so that we can make good predictions with the encoded representations. And also, with those encoded representations Q, we can't predict what the protected variable was. And in order to affirm this last point, we train a powerful adversary that tries to explicitly retrieve the protected variable from Q, but yet still fails. Okay, that's great. So how do we train this thing? We define a separate loss for the adversary, which is the difference between its predicted protected variable and the actual protected variable. Now, in training this architecture, we want to train the encoder, decoder, classifier components so that we maximize the loss of the adversary while minimizing the loss of the classifier and the decoder. We make this definition more rigorous in the next two bullet points, where we have a loss function composed of three terms, the loss of the classifier, decoder, and adversary. And our goal is to maximize the expected loss over h, which is the adversary, while afterwards, at the same time, minimizing the expected loss of f, g, and k, which are the encoder, classifier, and decoder respectively. Now, okay, what is this loss function? We use different loss functions for the different criterion we want to represent. Let's start with demographic parity. We're going to let di represent the dataset for when the protected variable z equals I. So for example, di could represent the partition of the dataset that only includes patients from a lower economic class. The loss function to uphold demographic parity in laughter is shown here. The outer sum is iterating over the possible protected variable classes, for example, high economic class and low economic class. For each one of these partition datasets, we're going to compute the average difference that the adversary guesses a protected variable versus the actual protected variable. And intuitively, this kind of makes sense, as this loss is going to be very high when the adversary gets many of those estimates wrong. And that's what we want here. Now we're going to talk about the loss function to uphold equality of odds. We're going to create a new definition for D, dij, and this is going to represent the dataset for when the protected variable z equals I and we're given a label y equals j. As an example, we can consider such a partition of the dataset dij to be the set of patients who are from a low economic class and also are healthy. The loss function to uphold this property is shown here, where the outer sum is going to iterate over all possible dij's, and the inner sum is going to also express that difference. And intuitively speaking, this is similar to the demographic parity loss function, except we're specifically considering the case where we know both the label and the protected variable class. Equality of opportunity has a very similar loss function as equality of odds, except now we're going to fix a specific variable j for the label. Again, we sum over these partition datasets that we have, and they're effectively computing the difference from the adversary versus the real truth value for all of those specific datasets that we select. Okay, so it looks like we have everything that we need to implement laughter. We have got the architecture, we know how to train it, and we know the loss functions. Now let's go back to our toy example, where we have our dataset X of X-ray images. We can pass our dataset through laughter, and laughter can give us a latent representation of this dataset Q. We know from before that expressing each data sample X as a data sample Q makes it very hard to get the economic status for that sample. Yet it's still very easy to classify and make correct predictions using Q. So we're encoding a very useful representation of X in this latent variable. For a more theoretical explanation of this architecture, do check out David Madras et al.'s paper on laughter. Thank you very much for watching.